Matrix multiplication. Now, with adding and subtracting, you can only add and subtract matrices if they're exactly the same size. Yeah, you can have an extra booklet. Now, we played around with multiplication yesterday, and they don't have to be the same size, not necessarily, but they do have to be compatible. And to be compatible, the columns in the first matrix have to be equal to the rows in the second matrix. So what does that mean? I can multiply a 2 by 3, okay, matrices rock, by, yes, a 3 by 1. Yeah, sometimes I do it that way, sometimes I do it. Okay, 3 by 1, again, this is matrices rock. And these middle numbers have to be the same. The number of columns, because we saw last time that these three numbers here, right, they get rotated and then blast into the other ones. So a row gets multiplied by a column because the size of your answer will be a 2 by 1. So you would multiply and have an answer here and an answer there. We'll do an example or two. So in other words, if A is a matrix of order k times m, and B is a matrix of m times n, these numbers in the middle are the same, so then it's possible, and then the size of your matrix that's the answer has to do with these outer numbers right there. So those middle numbers being the same is what makes them compatible in order to be multiplied. Anytime those middle numbers of the orders are not the same, you won't be able to multiply them. So let's look at the rules for multiplying. The middle dimensions must be the same, so this is fine because we have a 3 by 2 multiplied by a 2 by 1. Our middle numbers are the same, so yes, you can multiply these. If you look at this example, here we have a 2 by 2, and here we have a 1 by 3. Those middle numbers are not the same. So can we multiply them? No. No. Rule 2. If we can multiply them, then the resulting matrix will have dimensions of the outside numbers. So what does that mean? Well, this was a 3 by 2, and this was a 2 by 1. So our middle numbers were the same, and my outside numbers here become the dimensions of my answer, 3 by 1. So since the middle numbers are the same, we're allowed to multiply, and once we're allowed to multiply, we'll be able to tell how big our answer is by those outside numbers. Rule number 3, to get an answer, you multiply a row by a column and add. Well, we're going to color code things here. Okay? So, again, let's call this answer matrix M. Call the M. There we go. Again, I'm going to write this out every single time. So this is a 3 by 2 multiplied by a 2 by 1. These middle numbers are the same, resulting in a 3 by 1. In order to find element M11, so M11 deals with row 1, column 1. And what I like to envision is taking that 1, 2, turning it on its side, bringing it back, and blasting it in to the number. So you would get 1 times 7, and the 2 would hit the 8. Add them together, and you get 23. If you were finding the second one, and I'll do it in blue, M21. Well, the 2 is row 2, column 1. So to get that answer, you're going to have to take row 2, column 1. Again, I imagine taking row 2, turning it so the 3, 4 is on its side, blasting it into the 7, 8. 3 times 7 is 21. 4 times 8 is 32. Get those two answers, add them up, and you'll get 53. And finally, to figure out M31, well, that would be taking row 3, column 1, turn it on its side and blast it through. 5 times 7 is 35. 6 times 8 is 48. Add 35 and 48 together, and you'll get 83. So it's a complicated thing that's happening in that you're multiplying and adding, and we call this matrix multiplication. Tomorrow's lesson, we're going to see why do we do this, what kind of applications would this actually be helpful for. So that'll be nice. But right now, we're just learning the rules and trying to figure out what we're going to get. So here's a couple more examples. If those middle numbers are the same, then the answer is a 1 by 2. The second one, the middle numbers are not the same, right? You couldn't multiply a 2 by 3 by a 2 by 2, but you could multiply a 2 by 2 by a 2 by 3. Does that make sense? So the order makes a difference because those middle numbers have to be the same in order for it to work. All right. There you go, without a calculator.
I'm just checking my answers to see if I'm doing it right.
Should I put the first one up just to make sure you're on the right track?
Oh, yes.
There you go. Check how you're doing along the way.
Excuse me?
Yeah, it's 3 by 2 times 2 by 2.
Oh man, there it is. Okay, let's check. Did you get a squared right?
Yes, sir. Oh, I haven't finished that last one.
And we'll leave the last one for a bit. All right, here is the answer for the last one to check. And someone mentioned that they took AB and multiplied it by C, and this is what they got. And then someone else said they did BC first and multiplied it by A, and it worked out to the same thing. So based on what we've seen so far, we can talk a little bit about some of the properties. So we already know that you can't, just because you can do A times B does not mean that you can do B times A. And so we're going to learn some mathematical words that describe commutative. So the fact that 3 times 2 is equal to 2 times 3 in regular numbers means that regular multiplication is commutative. But in matrices, that is not the case. So in matrix multiplication, A times B is not equal to B times A. So here are some words. Commutative. Okay?
Wants to correct what you're saying.
Well, it's because I pushed enter so that it would be on the next line without, so it's just, here, make you want to be happier.
Yeah.
Okay, let's fix.
I drew a nice line.
There we go. That should be the right length.
That's perfect, thank you.
There we go.
Just worried. The fact that a teacher could be wrong scares me.
There we go.
It's a Keanu. Keanu Reeves. Keanu Reeves. I'm going to have to look at
Next math word deals with what we saw. Associative, what we saw in the last one. If you have three things multiplied and you keep the order the same, you can do the AB first or the BC first. It will work out to be the same. With matrices, you can distribute. Now, usually distribution is not recommended because from what we've done so far, what's easier, adding or multiplying? Adding. So wouldn't you like to add first so you only have to multiply once, as opposed to multiplying twice and then adding once? Yes, not.
What's the point of that law? Just to have it?
There is a multiplicative identity. Means there's something you can multiply by which doesn't change the matrix. It's like multiplying by 1 with numbers. 7 times 1, 1. 10 times 1, 1. That's that one with all the ones on the diagonal. So we're going to find out when you multiply by that. Let's just do a little test right now. When you multiply by that, so if I have 2, 3, 1, 0, 6, 5, which is a 2 by 3, if I wanted to multiply, what I need to multiply is a 3. All identity matrices are square matrices, so what happens when you multiply by this one? The answer is going to be a 2 by 3. Okay? And look, row 1 times column 1. The only number that hits is the 2. And the other ones are 0. Add them up, you get 2. Row 1, column 2. The only one that hits is the 3. And then, hey.
Just because it looks cool. Because it's cool. Stop complaining.
It's being able to multiply by 1. Okay? And it will be in that eventually this is going to connect to this idea with the inverse. If you multiply by the inverse of, if you can find the inverse of a matrix, they'll equal 1. So how do you find that?
Well, how can your matrix equal 1?
Well, this is 1 is this. When we talk about 1 with matrices, they're identity matrices. So if you multiply something by its inverse, everything cancels out and you get a 1. And whether you multiply an inverse in the front or an inverse in the back, you get the same answer.